Gases, their laws, and kinetic molecular theory of gases, KMT. Changing the volume of a container has no effect on the properties of a solid because that solid only has contact with limited surfaces of the container, as does a liquid. A gas, however, changes shape with changes in its container's shape and is affected by changes in that container's volume. When a gas particle comes in contact with the walls of a container, it exerts a force on that container known as pressure. Pressure is equal to force over area, so as area increases, pressure decreases, and vice versa. It can be difficult to measure the pressure of gases that surround us, but we can do so with a Torricellian barometer. The barometer consists of a glass tube filled with mercury sitting in a mercury reservoir. The gas that surrounds the barometer presses down on the mercury in the reservoir, forcing it up into the barometer. Pressure increases with decreasing altitude as there are less particles in the air to collide with the surface of the mercury at higher altitudes. The vacuum that forms at the top of the tube, measured in millimeters mercury or in mercury, represents the pressure of the air. Occasionally, millimeters mercury is represented as 1 torr, or indicated in atm. 1 millimeter mercury is equal to 1 torr, and 760 torr is equal to 1 atm. Unlike solids and liquids, gases are compressible. They can be confined to small volumes or expanded to large volumes. Boyle's law states that as the pressure P on a gas increases, the volume V decreases, and as the pressure P on a gas decreases, the volume V increases. Volume and pressure are inversely related, so as one increases, the other decreases. For volume and gas specifically, this can be written as P is proportional to 1 over V. With the gas proportionality constant K, which is unique for each gas, Boyle found that the volume V of a gas is equal to K over P. This equation can be rewritten as V is equal to K over P, which allows us to compare the volume of a gas over time. In other words, the volume V of a gas in current conditions multiplied by the pressure P of that gas in those same conditions is equivalent to its proportionality constant, which will also be equal to that gas's volume and pressure in a set of different circumstances. Often you will know 3 of these variables to find the 4th. The initial volume and pressure, for instance, along with the final pressure, can be used to find the final volume. The gas proportionality constant is not necessary to solve equations like these. Here's an example of an application for Boyle's law with changing pressure. If asked, a gas has a volume of 6.85 liters at a pressure of 0.658 atm, what is the volume of the gas if the pressure is decreased to 0.435 atm? You can assume that the temperature and moles of gas are constant, so you can use Boyle's law P1V1 equals P2V2 to find the proportional volume of the gas in changed conditions. As the temperature of a gas increases, the kinetic energy of that gas's particles increases, resulting in increased collisions with the walls of the gas's container. This concept is entitled Charles' law. Importantly, this law represents the first accurate prediction of absolute zero as a temperature, and this law states that as a gas's temperature T increases, its volume V also increases, and vice versa. V is proportional to T. The ratio of volume V to temperature T is directly proportional, unlike the ratio of pressure and volume. Gay-Lussac's law combines Charles and Boyle's laws by explaining the relationship between temperature and pressure, saying that pressure P and temperature T are directly proportional. As temperature T increases, pressure P also increases, and vice versa. The final ideal gas law is referred to as Avogadro's law. For any gas at standard atmospheric pressure and temperature, the number of moles of gas N is proportional to the volume V of that gas. This law also leads to the ideal molar volume of gas. At standard temperature and pressure, 1 mole of gas has a volume of 22.4 liters. For pressure, R has a value of 0.0821 atm, for volume, liters, for moles, mole, and for temperature, Kelvin. Because it can have so many different units, R is frequently notated as 0.0821 liter atmospheres per moles Kelvin. R is used in the ideal gas law, which states that pressure P times volume V is equal to the number of moles N of a gas times R times that gas's temperature, PV equals nRT. According to the kinetic molecular theory, or KMT, of gases, gases are composed of very small particles traveling at high velocities. Because of this, there is a lot of space between those particles, which means that they can easily be compressed or mingle with particles of other gases. The negligible attraction and repulsion between those particles also contributes to gases' compressibility because the particles cannot resist it. Furthermore, gas volumes are consistent over time because there is no notable loss of energy among their particles during collision. These particles are in constant motion and exert pressure on the sides of their container, which is why gases take the shape of their container. However, those collisions are highly elastic. In other words, most or all of the particle's kinetic energy is maintained even after the collision is complete. Finally, with an increase in temperature of a gas comes an increase in particle velocity, which explains the direct proportionalities between temperature and pressure and temperature and volume. And that is KMT and the gas laws.